Alright guys, so I'm making another video here. This time I am making it on homework question 2 for homework 4. Like I said in the last video, this is for an E&M class, and this is one way I upload my homework, the group portion of my homework at least. So that's really the main purpose of this, but if somebody else wants to, that's not in the class, wants to watch it, they're obviously, no one's stopping you, nor would I want to. But that's kind of my goal and what I'm doing here. So go ahead and get started. This is problem 2. And it says, on a given surface S that's bounded by a volume T, the electrostatic potential that takes a constant value V naught. The total charge inside the volume T is Q, and there's no charge anywhere else. So the electrostatic constraint in the space outside of S is that B wants us to find the energy required to assemble a solid sphere of radius R in charge Q. And then C wants us to do the exact same thing, or not the exact same thing, but I guess similar, to find the energy stored in the electric field. So part A is a bit of a proof. We ultimately need to get to this stuff. Okay. So the work to assemble a collection of point charges, so the work to assemble, supposed to be an S, a collection of point charges. And for the record, if you wanted to just skip some of this, you could, but I'm trying to show as much of the definition as I can without making it ridiculously long. So like we talked about in class, if you are bringing charges in from infinity to this point, the first charge you basically get for free. There's no other charge acting on it, so for the first charge, there's no work. And we'll just call this work 1. Now work 2, if we're to bring a second charge in, you'll have your charge there, 4 pi epsilon naught times the charge that was put there for free, because that's now actively working against it, over the separation vector from 1 to 2. And you could keep doing this, and the book does it, I think, 3 or 4 times, but at the end of the day, I think you can kind of see what's happening, and we're getting a summation. 1 over 4 pi epsilon naught, that's a constant. And then what do we have? We have a double sum here. And this will go from I equal 1 to n charges, to j greater than I, n charges, q sub I, q sub j, over our separation vector ij. Okay? So the fact that j is greater than I, all that means is we're bringing in another charge, right? So like for the first example, we brought in charge 2. If we brought in a third one, then it would be charge 3, and so on and so forth. Another way to do this, which is what the book does, is it purposely counts each pair twice and then just divides by 2. So it's kind of an interesting way to think about it, that if you add up all your charges, including, it's basically doing them twice, so you're not even really worried about this so much, and just divide by 2, you also get your answer. So divide by 2, that 4 becomes an 8. We still have our, that should be 4 pi epsilon naught, I to n, okay. So the only thing this is doing now, it's obviously I can't be j, because you can't, a charge isn't going to do work on itself, right? That doesn't make a whole lot of sense, but so that's all that's doing. And the equation for our work is 1/2 the summation of I n q sub I times the summation, and this is for j not equal to I, n 1 over 4 pi epsilon naught times q sub j script rj. Okay, so the 1/2 is now here, which left me with the 4 pi, which I then just went ahead and distributed, and I have the qi right here. So that's all that is. Now, why did we do this? That's because this is just v, our potential, which you can get by some function of r. Sorry. Sorry about that. So that's why that's written the way that it's written. So you get 1/2 the summation I equals 1 to n q sub I, and now we have our potential. Okay. Now you could also write this as an integral if you're doing an infinite sum. And this just becomes dq v of r. Okay. Hopefully that's okay with everybody. And dq we can simply rewrite, because dq is your charge density times, we'll just say d tau, or volume. So then we get the equation we get in the book, which is 1/2 integral of rho times our potential times d tau. Okay. So again, if you really wanted to, you could just go in the book and get your equation. But at least for me, it helped to actually see a little bit where all this stuff is coming from. Okay. Now, the charge density, if you remember from Gauss's law, the divergence of our E field is our charge density divided by epsilon naught. And solving for our charge density, we get epsilon naught times the divergence of our E field. Okay. So this is our rho. I can substitute that in there. So then we get our work is going to be simply 1/2. There's an epsilon I can pull out now, so the epsilon will come out. The integral, this is an integral over some volume. The divergence of our E field. And then we still have v d tau, also just kind of hanging out there. All right. Now, this next part, I want to remind us something from chapter 1. This is our integration by parts. So the integral of a volume of f, the divergence of vector A, d tau, is just equal to the closed surface integral of some function times our vector A dotted with our area vector, or our dA, minus the integral over a volume of A dotted with the gradient of f dv. Okay. So this is equation at the end of the book, something we used in one of our homeworks, and we're going to use this here because this is pretty much, I mean, I'm sure you can see how, maybe if I move V over here, I didn't mean to do that. I mean, I'm sure you already see it, but that's a spitting image of that. So we can expand it using what we have there. So epsilon over 2, we can't forget that. That's going to be out there. And then what do we have? We have the surface integral, which the surface is called, I think just S. I know the volume's T, so I think this is just S. S of, and let's just see that our F is basically our potential, and vector E is basically our vector A in this general example. Okay, so we have the closed surface. Oops, I'll move it down a little bit here. Epsilon naught over 2 times, the first thing is we have the closed surface integral of f, that's going to be v naught because that's along the surface, E dot dA, okay, minus the integral over some volume, which they're calling t, our E field times the gradient of v, dv. Okay. Well, v naught's a constant, so I can pull that out. So I get epsilon naught over 2 times v naught, the integral, the surface integral, the closed surface integral of E dot dA minus the volume integral of E dot. Now, if we remember, our electric field is simply the gradient of our potential. So I could replace that with vector E dV. And, well, we'll get there in a second. So this part should look a little bit familiar. A closed surface integral of E dot dA. That is just Gauss's law. And we know that the closed integral of E dot dA is just our Q enclosed over epsilon naught. Okay, so we have epsilon naught over 2 V naught times Q enclosed, which is just Q, over epsilon naught, minus the integral over our volume, E dot E, that's just the magnitude, E squared dV. Okay. Now for part A, it wants to show that the electric static energy contained in the space outside of S. So for that, we're only interested in this first part here. Okay, and if we distribute that, your epsilon naughts cancel, and what are we left with? Q over 2 epsilon naught. That's part A. Okay. Part B. Part B says, using the potential formulism of that, find the energy required to assemble a solid sphere of radius r and charge q. Okay, so what do they tell us? They tell us that UE is the triple integral of V dq. Okay. Well, we know what V is, right? V would be our potential Q over 4 pi epsilon naught r. That's our potential for a sphere. So we can plug that in. And you get Q over 4 pi epsilon naught r dq. I'll make these integrals a little bit bigger here. Okay. Okay, so we have that. Now, I think you can see from here that our du is simply then going to be, well, first off, we need to find what Q is, right? So Q is going to be our density, rho, times the volume, 4/3 pi r cubed. And if we wanted to find, I guess, little dq, same idea. Take the derivative, and you get rho times 4 pi r squared dr. So we have a q, we have a dq, and we can plug that in. You could imagine that our du, by taking the derivative, we just plug everything we have in there. So we're not worried about the integral in this part. And let's see, so you got to plug in your Q and your DQ, and you get 4 pi rho squared r to the 4th over 3 epsilon naught dr. Okay, so that's just substituting our Q and DQ in. Then our U is going to be simply, well, it's only a factor of dr, so everything else is a constant. 4 pi rho squared over 3 epsilon naught. And then we will integrate r to the 4th dr. And we'll just call it from 0 to big R. We'll let r be the radius. I don't know if it mentioned it, but suppose it doesn't matter too much. You obviously get 4 pi rho squared over 3 epsilon naught times 1/5 big R to the 5th. And we can plug these stuff in. So you will get rho squared. We need rho squared, right? Well, rho squared is going to be our rho, which is, our rho is simply 3q over 4 pi r. Okay, so it's our charge by our volume. So then rho squared is 9q squared over 16 pi squared r squared. So this is our rho squared, and we can plug that into here as such. And if you do that, you will get 3q squared over 20 pi epsilon naught r. Okay. Oh, I'm sorry. This should be cubed, and then this should be to the 6th now, right? Because it's 4/3 pi r cubed. Totally missed that. I was looking at my work. I'm like, that's actually not. How did I get that? So there we go. And that's it. That's all there is to do with that one. For part C, it wants us to find the energy stored in the electric field. So let's just draw a circle. And obviously it's got uniform charge density, whatever. And now we need 2 Gaussian surfaces. We'll let one be like this. We'll make that green. And then we'll make a red one. Let me try that again. It's a little bit better. Okay, so obviously the red one is the outside, the green is the inside. So what do we have? We'll just say that this little one here, I'm going to erase this plus charge just so it doesn't get in my way. We'll call this R. And we'll call this the actual surface big R. So little r is our Gaussian surface here. Okay, so we need to find the E field both inside and outside. You probably already know how to do this. I'm going to do it just because this helped me. And if you don't remember, this has been a major pitfall for me, so this is why I'm doing it. With Gauss's law, I get my E's wrong all the time. All the time. Or my R's, not E's, my R's. So that's why I'm doing this, partly for my own sake to practice, but then if it helps other people, then that's fantastic. Okay, so our E times 4 pi little r squared is equal to Q, and basically what we have is a ratio of 4/3 pi r cubed divided by 4/3 pi big R cubed. So basically what we're doing is we're doing a ratio to find how much charge is actually inside this part. And obviously the 4/3 and the pi's drop, and you're left with that. And solving for our E field, I guess this is the magnitude. The magnitude of our E field then is going to be Q R divided by 4 pi epsilon naught big R cubed. And this is for R less than big R. Okay, so that's the E field. Now we also need the E field outside. So for little r greater than big R, it's going to be the same idea. This is our E field inside. E field times 4 pi r squared. Well, now the charge enclosed is just Q over epsilon naught. And then solving E out is equal to Q over 4 pi epsilon naught little r squared, which is entirely what we expected. It looks like a point charge out there almost. The E field from a point charge. Okay, so we have our E field is equal to QR over 4 pi epsilon naught big R cubed and Q over 4 pi epsilon naught little r squared. This is for when R is less than or equal to big R. This is when R is greater than R. Okay. Now from part A, we saw that our U is epsilon naught over 2, the integral of our E field squared dV. Right? Okay, so we can write U1, so this could be inside, for example, is epsilon naught over 2. We'll integrate from 0 to R, E squared, times the surface area of our Gaussian, which is 4 pi r squared, and then dr for the thickness there. And this is pretty easy to solve for, right? We'll get epsilon naught over 2 from there, and then times 4 pi e squared, the integral from 0 to r squared dr. So all we have to do is integrate that by adding 1 and then dividing by it. And if we do that, we should get that our E field, our E field, well, first let's do, actually, no, this is wrong. I'm sorry. I made a mistake here. I know what I did wrong, though. So pitfall, perfect. Perfect pitfall to call out. Our E field squared is equal to Q squared R squared over 16 pi squared epsilon naught squared R to the 6, because it was cubed. And now what I should have done and what I was doing wrong is I need to plug that into here, because our E field changes depending on how far into the sphere we are. So that was a major pitfall to watch out for. Okay, fair enough. So E naught over 2 times Q squared 4 pi over 16 pi squared epsilon naught squared R to the 6, the integral from 0 to R, and now this is going to be R to the 4th, because there was already an R squared, and we just added another one to that. The big R, that's just the radius of the sphere, that's not changing, so don't get that confused. That's another pitfall. We can simplify this a little bit here. Okay. And we get Q squared over you're going to get a 40 pi epsilon naught r, because we're also going to have to add one here. So you're going to get 8 times 2 is 16. And then you're also going to have to deal with the 5 and then divide. So that, I think, is what we would get there. And then for U2, it's actually a little bit easier. U2 is going to be outside, so that's going to be epsilon naught over 2. The integral from our surface all the way off to infinity, e squared times 4 pi r squared dr. This is exactly like before, just changing our bounds a little bit. And we know what e squared is, so you can plug that in, factor it out, you'll get q squared, q squared over 8 pi epsilon naught, the integral from r to infinity of r to the negative 2 dr, which will get you q squared over 8 pi epsilon naught times negative 1 over r evaluated from r to infinity. And then obviously if you put infinity in the denominator, that's 0. So minus 1 over capital R turns that positive, so the negative sign's taken care of. You get q squared over 8 pi epsilon naught r, and that's my U2. Now my total energy would just be U1 plus U2, which is right there. So let's see, q squared over 40 pi epsilon naught r plus q squared over 8 pi epsilon naught big R. So let's see, basically what we're doing is 1/40th plus 1/8. So multiply it by 5, right? 8 times 5 is 40, I think. So this is 1 over 40 plus 5 over 40. So that's 6 over 40. 2 goes into both, 3 over 2 times, right? 20 times, not 2. Okay, so then U total is then just 3q squared over 20 pi epsilon naught r. And that's it. That's the energy in your E field. I think, I could be wrong, but I gave it a real effort. I gave it a real try. I did my very best. Pitfalls, you can see with my E field, that was a major pitfall to keep in mind. So I would watch for that. There is alternative ways to do these problems. I think with the first one, you kind of have to just do it that way. The way that we did it with the proof, but maybe not. I don't know entirely. But yeah, that was the way I approached it. Obviously, I try to mention the pitfalls. Alternative ways. Let me see if I can think of any real quick. You could probably not integrate over dq. I think what you could do, if you wanted as an alternative way, I didn't, but I think you could. You could say dq is equal to rho dv, and then integrate over v. So I think that's an alternative way you could have solved this, as well as C. Or at least B you could. So I think that's everything. Hopefully that helps out.